now the derivative. And again, we're only going to do the derivative of the exponential function base e and the natural log, so the log function base e. All right? If we look at the other types, it's actually more difficult. And so we don't do them in this class because we can always convert to base e. All right? So all of our stuff we're going to do in this class will be the natural number e. Now, the reason why is because the natural number e itself is defined by a limit. Right. The e, which again is an irrational number like pi, shows up again, we call it the natural number because it's whenever we have exponential growth or exponential decay, which models, again, most populations, money, and things tend to grow exponentially. Right, so it occurs in nature, naturally, just like pi. Pi occurs in nature, it has to do with the circle and angle measures. And so e, this natural number e, is actually defined by the following limit. Limit is h approaches 0, 1 plus h raised to the 1 plus h. You plug a really small number in there, it gives you the e. That's actually what your calculator's doing when it finds the e number. Which again, irrational means it's a decimal that's forever, like pi, never ends, never repeats. Alright, and so there's two we're going to look at. There's the, again, we'll start off with the first one, which is the f of x is a e. A is just a number like 2 e to the x. This would be a growth model. And then when we have a negative up here in my exponent, this would be the decay model. I'm decreasing in that model type. And again, you should have talked about this in an algebra class. Because the natural number e itself is a limit, and remember, in a limit, look at it, it involves that h approaching 0, which the derivative is, remember the derivative is h approaches 0 of the average rate of change. Because of that, and because of the way exponential growth and decay works, the derivative is actually really nice. But sometimes it's so easy it's hard because students want to overthink these. Alright, so the derivative of the a e to the x, so this is the one with just x up there, so it's just the growth model case. Alright, so again, when I want to take the derivative of f of x, where a again is just a real number value, e is our, base e is our natural number raised to some variable x. When we take the derivative of that, it is the original expression. Whenever you talk about exponential growth and exponential decay, we say that exponential growth and exponential decay are models that grow at a rate proportional to their size. Right? So the derivative is the original function, meaning f of x is growing at the same rate, right, that's what the derivative is, as its size. Right? The size would be the f of x value. So again, if I just do a simple example, f of x is 2e to the x. The derivative itself is 2e to the x. So at 1, it's 2e. That's the size, right? Whatever this model represents, it's 2 times the e value. It's growing at a rate of also 2e. Right? That's how fast it's growing. And then at x equals 2, the size would be 2e squared, and it would be growing by 2e squared. It's exponential growth. So it's growing faster. It's growing at the same rate that it's growing at the same size. Alright, so that's what we mean by growing at a rate proportional to its size. And so when we take the derivative of the e function, it is just literally whatever the original function is. Now, that is when it's just e to the x. Where things get more complicated is when you've got something other, and it can be anything other than x up there. Alright, when it's something other than x, it's a function of x, which can be as simple as negative x, right, because that's a function of x. I've taken negative 1 times x, is no longer just x. We have to involve the chain rule. Alright, so the chain rule and the exponential function. Alright, so our g of x is differentiable. So again, and so what this is this involves the chain rule. Remember, the chain rule is the derivative of the outside, leave the inside, and then separately we multiply by the derivative of the inside. Well, the outside is the e term, right? The e function. The inside is whatever that g of x is, whatever that x expression up here in my exponent is. And so when we take the derivative of something where there's e raised to something other than just x, the first thing you do is you write down the original expression, because that's the outside part. The derivative of the e function is the e function. So you write down verbatim whatever that original expression was. But since there was something other than x here, you've got to then remember to multiply that expression by the derivative of whatever that something was. Right? And again, like I said, it could be as simple as the decay model, 2e to the negative x. But since we've got a negative up here, the chain rule applies. The first step is to write the original function down, 2e to the negative x. But then I'm not done yet. The decay model, remember, decay means decrease. So the derivative should come out negative. The only way to get a negative out is to remember I've got to multiply by the derivative of the inside. Well, so I just looked, so g of x in this case is negative x. That's the function I look at. Well, the derivative of negative x is negative 1. And so that derivative is negative 2e to the negative x. And that's the chain rule. All right, so again, whenever there's something, anything up here but x, so it can be just something as simple as a number times x, I have to use the chain rule because I'll have to multiply by that number. All right, so we'll pick up some examples in the next video. So I'll go over some examples of this.